Discuss the remaining questions of Riemann integration. So the next question says that show that the function fx, which is sin x, is integrable on any interval 0 to t. And in the question itself they have given us the partition P, and we are supposed to show that this integration is equals to 1 minus cos t. So first let us show that the function is Riemann integrable on any interval 0 to t. So the partition P is given to us as 0, t by n, 2t by n up till nt by n, and we know that the function fx, which is sin x, is bounded. Mod of fx is always less than or equals to 1 for all x belonging to 0, t. So from here we can conclude that the function fx is bounded for all x belonging to 0 to t. Also sin x is basically a continuous function. Fx is continuous function, and we know that a continuous function is Riemann integrable, and a continuous function is Riemann integrable. So from here we can conclude that our function fx is basically Riemann integrable. So this is the first part of question that asks us to show that the function is Riemann integrable in any interval 0 to t. And the other part is we are supposed to show that this integration is equals to basically 1 by t. Now since this is Riemann integrable, let's assume another function. Let's name it as gx as minus of cos x, and it is defined for all x in interval 0, t. Now if you observe that this function gx is continuous and differentiable on interval 0 to t, and also it satisfies this property, that is differentiation of gx is equals to fx, and it holds for all x in closed interval 0 to t. Now if we use fundamental theorem of algebra, using fundamental theorem of algebra, we'll get that integration from a to b fx dx is equals to g of b minus g of a, where g dash of x is equals to fx. So using this result on the fx and gx that we assumed, so we'll get that integration from 0 to t ft dt, or let's just write that sin x dx is equals to g of t minus g of 0, and we have assumed gx as minus of cos x, so it will be minus cos t minus of minus cos 0, and cos 0 is 1, so it is equals to 1 minus cos t, and that's what we are supposed to show. So we got that integration from 0 to t sin x dx is equals to 1 minus cos t, and this is the relation that we are supposed to prove. Also in this question, like since it's a 10 marker, so we are able to directly use the relation that gx is a continuous, like fx is a continuous function, and we know the result that continuous function is Riemann integrable. But if it, let's say it's a 15 marker, then you are supposed to prove that a continuous function is basically Riemann integrable. In that case you cannot directly say, like you cannot directly use that result. So in that case you'll take partition and show that a continuous function is Riemann integrable. So let's move on to discuss the next question. So the next question is, they have given us a function fx as this, and we're supposed to check if this is Riemann integrable on interval minus 1 to 2, and we are also supposed to tell the reason why it's Riemann integrable, and also they have asked us that does there exist a function g such that g dash of x is equals to fx. So let's see how we can do this. So the first condition for a function to be necessary condition for a function to be Riemann integrable is that it should be a bounded function. So let's check first that if a function is a bounded function or not. Since our x lies in between closed interval 0 to -1, so I can write this from here. So from here x square will lie in between 4 to 0 and x square by 2 will be this. And if I just add in 4 on both the hands, so it will give me 4 less than or equals to x square by 2 plus 4 less than or equals to 6. So I got that whenever x is greater than 0, this is a bounded function. Likewise, when x is less than 0, so I got my x square for all x in between this, I got my x square as less than or equals to 4 and greater than or equals to 0. So from here my x square by 2 will be less than or equals to 2 and greater than or equals to 0. And if I just multiply it by -1 throughout, so it will be 0 greater than or equals to minus x square by 2, that is greater than -2. And if I just add in 2 on both the hands, so it will give me 2 less than or equals to 2 minus x square by 2 greater than or equals to 2 minus 2, that is 0. So from here I got that whenever my x is less than 0, then also my function fx is bounded. So using this I can claim that I have shown that my function fx is a bounded function. Now let's check if we can use some result. So if you observe that it's a function defined on parts, so if you observe that this part is continuous in itself being a polynomial function, likewise this is continuous in itself being a polynomial function. So the only point of discontinuity that can exist is basically at x equals to 0. So let's check if the function is continuous at x equals to 0. So limit x approaches 0 negative of fx, that is if we approach 0 from left hand side, it will be equals to limit x approaches 0 minus x square by 2 plus 2. So this is equals to 2. Likewise, when limit x approaches 0 from right hand side, so it will be equals to limit x approaches 0 x square by 2 plus 4. So it is equals to 4. Now if you observe that the left hand limit is not equals to right hand limit, so my function fx is not continuous at x equals to 0. So function fx has a discontinuity at x equals to 0, and except this point x equals to 0, the function fx is continuous at all other points. So we have discontinuity at only finite number of points. So we have a result which says that if a function is continuous elsewhere except at finite number of points, then the function is Riemann integrable. So using that result, I can claim that the function fx that is given to us is a Riemann integrable function. Number of discontinuities is finite. And using the result which says that a bounded function f having finite number of discontinuities on a closed interval a comma b is Riemann integrable. Riemann integrable on closed interval a comma b. So using this I can conclude that my function fx is basically Riemann integrable on closed interval -1 to 2. Riemann integrable on closed interval -1 to 2. So that's the first part of question, that we're supposed to show that, check if it is Riemann integration or not, and we have given the reason as well, because the discontinuity is finite, so it is Riemann integrable. Now we are supposed to check if there exists a function g such that this holds. Now if I since the function we got that fx is Riemann integrable, so if I assume my gx to be, let's say, x cubed by 6 plus 4x whenever x is greater than or equals to 0, and minus x cubed by 6 plus 2x when x is less than 0. So in this case, for this g, if you see that this relation is satisfied for all x lying in between minus 1 to 2. So from here we got that there exists a function such that this relation holds, and this function exists because the function is Riemann integrable. And if we find its value, like find the value of a function that it will attain after the integration, so it will be equals to g of 2 minus g of minus 1. Now since 2 is greater than 0, so we'll use this part, so it will be 2 cubed by 6, that is 8 by 6, plus 4 times 2, that is 8, minus g of minus 1, and minus 1 is less than 0, so we'll use this part, so it will be minus of minus 1 cubed by 6 minus 2, and this simplifies to 4 by 3 plus 8 minus 1 by 6 plus 2, and that is equals to 7 by 6 plus 10, that is 67 by 6. So 67 by 6 is the value that the function fx attains after the integration. So let's move on to see the next question. So the next question is, let x denote the integer part of real number, that is f. Okay, so it is basically a greatest integer function only. Then here they have defined what this notation means, and it is of a greatest integer function. Then they have asked that, is this function fx a Riemann integrable on closed interval minus 1 to 2? And if it is not, then we are supposed to give the reason, and if it is integrable, then we are supposed to compute this. Now let us define this f of x on this interval. So f of x is basically x square plus 3 on interval minus 1 to 2. Now if you observe that the only point of discontinuities for our greatest integer functions are the integer points. So if I just define this function fx, so for a greatest integer function, only point of discontinuities are at integer points. And if you observe that in this interval, in minus 1, 2 interval, there are only finite number of integer points. There are only finite number of integer points. And since there are only finite number of integer points, so the number of discontinuities that this function fx has is finite. So number of discontinuities fx has is finite. So, and we have, like in the previous question only, we used a result that if a function is a bounded function which has discontinuities at finite number of points, then that is Riemann integrable. So using that result, I can claim that my function fx is a Riemann integrable on closed interval minus 1 to 2. Also, you were supposed to show that this is a bounded function, so let's do that as well. Like fx is equals to x square plus 3 on minus 1 comma 2. So the greatest value that this mod x is less than or equals to 2 for all x in closed interval minus 1 comma 2. So from here mod x square, the greatest integer function square, will be less than or equals to 4, and if we just add in 3 on both the sides, so from here we'll get that our function fx is less than 7 for all x in interval minus 1 to 2. So from here we got that the function fx is a bounded function, and since it's a bounded function and has discontinuities only at finite number of points, so we can claim that we got that the function fx is basically Riemann integrable. So that completes the first part. Now we're supposed to compute this integration as well, so let's do that. So one way to do is you can compute upper Riemann sum and lower Riemann sum, or other way to do is you can do that directly as well. Like if I calculate, let's say, upper Riemann sum, so it will be equals to summation I equals to 1 to, or let's take a partition only. So let P be my partition and it is equals to, and so on up till xn and then y0, which is I am assuming to be 0, y1, y2, and so on, and then yn is equals to, let's say, z0, which is equals to 1 less than z1, and so on up till z2, which is equals to up till zn, which is equals to 2. So I have taken these three notations, that is xi, yi and zi, so that I can just make the partition specific to the integer points. For example, if this is my interval, so this xi are the partition of this interval minus 1 to 0. Likewise the yi's are partition of 0 to 1, and zi's are the partition of 1 to 2. And I have done so because the greatest integer function will have same values in this interval and this interval as well. So in order to prevent so in order to use that information, I have taken these as partition. So my upper Riemann sum will be equals to maximum of the function fx in this interval plus multiplied by the size of this interval, that is 1, that is mr delta xi, that is in this interval, plus mr dash times delta yi plus mr double dash in delta zi. Now size of each interval is 1 only, so it will be equals to mr plus mr dash plus mr double dash, and the greatest value the function can attain in this interval is, if you observe in this interval minus, if x lies in between this interval, so the value that it will attain is this. So it will be, let me just write my function fx only. So my function fx is equals to, when x is in this interval, it is minus 1 square plus 3. When x is in this interval, it is 0 square plus 3, and when x is in this interval, it is 1 square plus 3. So it will be 4 plus 3 plus 4, that is 8 plus 3, which is 11. Likewise, if you compute lower Riemann sum, it will be equals to small mr into delta xi plus small mr dash into delta yi plus small mr double dash into delta zi. And here also the size of interval in each case is 1, so it will be equals to mr plus mr dash plus mr double dash, and in this case again it will be equals to 4 plus 3 plus 4, which is also equals to 1. So since from here also we got that our upper Riemann sum is equals to our lower Riemann sum, so from here my function fx is Riemann integrable. Now you can solve this, that is minus 1 to 2 fx dx as this as well, like minus 1 to 0 fx dx plus 0 to 1 fx dx plus 1 to 2 fx dx, and in this case it will be equals to minus 1 to 0 4 dx plus 0 to 1 0 plus 3 dx plus 1 to 2 4 dx. So it will be 4 times 0 plus 1 plus 3 times 1 minus 0 plus 4 times 2 minus 1, that is 4 plus 3 plus 4, which is equals to 11. And that's what we got our upper Riemann sum and lower Riemann sum as well. So this completes this question as well. Let's move on to discuss the next question. So the next question says that if fx is a function differentiable on closed interval 0 to 1, and it is like this function fx holds these properties as well, then we are supposed to prove that this relation holds. So let's see what all information is given to us. So fx is a differentiable function, and since it is a differentiable function, so from here we can conclude that fx is continuous as well on closed interval 0 to 1. Also the information that is given to us is that f of 1 is equals to f of 0, which is equals to 0, and integration from 0 to 1 f square x dx is equals to 1. Now we are supposed to show that integration of this function, that is 0 to 1 x fx times f dash x dx is basically equals to minus 1 by 2. Now if you observe that, you can just apply integration by parts in this question, and we are able to integrate it because this function fx is continuous, and a continuous function is basically integrable. So from here we concluded that fx is integrable because a continuous function is Riemann integrable. So since function fx is integrable, also this x function is also continuous, so x of fx is continuous. Let me write it here, x is also continuous. So from here x of fx is also continuous, and since fx is differentiable, so x of fx will also be differentiable. So using that we can just integrate it. So from here x of fx is also integrable. So now let's use this information to integrate it by parts. Let's name it as first part and this as second part. So while we do integration by parts, we keep first function as same and we integrate second function, so that will be equals to x fx integration from 0 to 1 f dash x dx minus differentiation of first function and integration of second function and then whole integration of this thing. So if we just solve it, this will be equals to, that means this term will be basically equals to x fx times f of 1 minus f of 0, because its integration will be fx only, and from here we'll get integration from 0 to 1. If we differentiate it, it will be equals to fx plus x f dash x, and by integrating it we'll get f of 1 minus f of 0. Wait, here limit won't be there, like it will be integration of f dash x dx. So from here we'll get fx only, and then we integrate this whole thing with respect to x. So it will be equals to x times f of x and in the question they have given us that f of 1 is 0 and f of 0 is also 0, so this term will be 0 minus 0, that is 0, minus integration from 0 to 1 fx square plus x fx f dash x dx. Now I can write it as this whole term will become 0, so it will be equals to minus integration 0 to 1 fx square dx minus integration 0 to 1 x fx f dash x dx. And if you see it clearly that this is the term that we are integrating, so we can just take it on the left hand side, so it will be 2 times integration of 0 to 1 x fx f dash x dx will be equals to minus integration from 0 to 1 fx square dx. And in the question they have given us value of this term as 1, so it will be equals to 2 times integration 0 to 1 x fx f dash x dx is equals to minus of 1. So from here it will be 0 to 1 x fx f dash x dx will be equals to minus 1 by 2, and that's what we're supposed to prove in this question. So in the question the main part is to justify why we are able to integrate this function f like this term. So that is there comes the concept of Riemann integration. So let's move on to discuss the next question. So the next question asks us to show that it asks us that give an example of a function fx that is not Riemann integrable but mod of fx is Riemann integrable. So there are many examples to this function. So the easiest can be the Dirichlet function that is defined as 1 when x is rational and minus of 1 when x is irrational. Now this Dirichlet function is not continuous anywhere, so fx is discontinuous for every x. For all x in, let's define it on interval a comma b for convenience. So it is not continuous. You can show that it is not continuous, and then further you can show that it's not Riemann integrable as well, because if you'll calculate its upper lower sum for any partition P, that you'll get as 1, and if you calculate its lower Riemann sum, that will be minus 1. So no matter what partition you choose or what epsilon you choose, you cannot make difference of upper Riemann sum and lower Riemann sum arbitrarily small. So since UPF is not equals to L, so from here fx is not Riemann integrable. But if we calculate the modulus of function fx, so it will be equals to 1 for all x in interval a to b. Now this is a constant function and we know that a constant function is Riemann integrable. Mod of fx is constant function and a constant function is Riemann integrable. So from here we got that our function mod of fx is Riemann integrable. So this completes this part as well. Now let's move on to discuss the next question. So this is a repeated question. We have discussed it in previous video. We'll get a function gx as something like this, x square sine 1 by x, and then we can use fundamental theorem of calculus, and using that we can show, like from here this function gx will hold this relation, and then we can use fundamental theorem of calculus. Also by mistake in the previous video I mentioned fundamental theorem of algebra, but that is actually fundamental theorem of calculus which we use in this relation. Fundamental theorem of algebra is about the number of roots that a certain polynomial can have. So let's move on to discuss the next question. So in this question they have given us a function fx, and this function fx is defined as f of x equals to 1 by 2 raised t when it is when x lies in between 2 raised t plus 1 less than x less than equals to 1 by 2 raised t, and it is 0 otherwise. Now this is also a repeated question. We have done a general case wherein our function fx is equals to 1 by a raised t when x lies in between 1 a raised t plus 1 less than x less than or equals to 1 by a raised t and 0 otherwise. So in that question, if you put a equals to 2, then this is basically particular case of that. So you can refer the previous video to see its solution. So it is also a repeated question. Let's move on to discuss the next question. So the next question says that show that the function fx is Riemann integrable in this interval, where this is the greatest integer function. And can you give an example of function that is not Riemann integrable on 0 to 2? Okay. So first let us show that the function fx is Riemann integrable on this interval 0 to 2. Now if you observe that this is greatest integer function and this is modulus, so a greatest integer function has discontinuities, like we have discussed this earlier as well, that a greatest integer function has discontinuities only at finite number of points. So the function also, this modulus function also has discontinuity, like it is continuous everywhere. So the only point of discontinuity that this function fx will have because of this greatest integer function. So greatest integer function has discontinuities only at integer points, and the integer points in this interval 0 to 2 are finite. So fx has discontinuities at finite number of points only. At finite number of points, and we know that if a function fx is continuous and has discontinuities only at finite number of points and is bounded, so that is a Riemann integrable function. So using that result we can conclude that fx is basically Riemann integrable. Now let's first find out this and then we'll give a example of function that is not Riemann integrable on 0 to 2. Now if we take a partition P as 0 equals to x naught less than x1 up till xn equals to 1 equals to y naught which is less than y1 and so on up till yn which is equals to 2. So let's assume this as our partition. Now if I define my function like fx, it will be equals to, fx is basically square, greatest integer of square plus modulus of x minus 1. So let's just partition it when x lies in this interval. So from here my x square will also lies in this interval. So from here x square also belongs to this interval. So if that's the case, this function will take value 0 plus minus of x minus 1, and when x lies in between this interval, so my x square will belongs to 1, 4. So in that case, like I again need to break that like in subparts. Let's do that, because when x square will lie from, like this can be broken as when x square lies in between 1 to 2, and then further when x square lies in between 2 to 3, and then x square lies in between 3 to 4. So let's just break our function fx as that. So it will be minus x plus 1 when 0 less than or equals to x less than 1, and when x will lie in between in that case it will be 1 plus x minus 1, that is x only. When x lies in between this, then it will be 2 plus x minus 1, which is 1 plus x, and when x lies in between this, so then it will be 3 plus x minus 1, that is 1 plus x. So our function fx is broken into these parts, that is 1 minus x when this happens, x when 1 less than equals to x less than square root of 2, 1 plus x, so square root of 2 less than x less than square root of 3, and 2 plus x when square root of 3 less than equals to x less than 2. Now let's see what will be the upper Riemann sum and lower Riemann sum. So UPF will be equals to, or we can just, like we have, since we have divided it, so we can just take integration, like we can just use integration on these subintervals. So integration from 0 to 2 fx dx will be equals to integration from 0 to 1 fx dx plus 1 to square root of 2 fx dx plus square root of 2 to square root of 3 fx dx plus square root of 3 to 2 fx dx. So if we just integrate it, it will be 0 to 1 1 minus x dx plus 1 to square root of 2 x dx plus square root of 2 to square root of 3 1 plus x dx plus square root of 3 to 2 x plus 2 dx, and on integration it will be x minus x square by 2 0 to 1 plus x square by 2 1 to square root of 2 plus x square by 2 square root of 2 to square root of 3 plus x square by 2 plus 2x square root of 3 to 2, and it will be 1 minus 1 by 2 plus 2 by 2, that is 1 minus 1 by 2 plus square root of 3 plus 3 by 2 minus square root of 2 minus 2 by 2, that will be 1, and plus it will be 4 by 2, that is 2 plus 4 minus 3 by 2 minus 2 root 3, and it simplifies to 2 minus, it will be 1 plus 1 2 minus 1, that is 1 plus square root of 3 minus square root of 2 plus 1 by 2 plus 2 plus 4 6 minus 3 by 2 minus 2 root 3, and that simplifies to 6 plus 1 7 plus half, that is 13 by 2, or it will be 15 by 2, sorry. And minus square root of 2 minus square root 3. So this is the value of integration that we'll get. Now in the question they have asked us to give a function, example of function that is not Riemann integrable on 0 to 2. So you can use Dirichlet function. So you can define Dirichlet function as fx as 1 when x is rational and 0 when x is irrational on 0 to 2. So this function is discontinuous everywhere, so it will not be differentiable, it will not be Riemann integrable. Now let's move on to discuss the next question. So the next question is, check whether or not the following function is Riemann integrable or not. So the given function is fx equals to sin x by x when x is not equals to 0, and it is 1 when x is equals to 0. So if you observe that sin of x is less than x for all x, So from here we can say that sine of x by x will be less than 1 for all x in 0 to 1. So from here we got that our function fx is less than 1 for all x in, sorry, it's minus 1 to 1 because the domain is minus 1 to 1. So fx is a bounded function. That is a necessary condition for a function to be Riemann integrable. Now let's see. We know that the function that is limit x approaches 0, fx will be equals to limit x approaches 0 sin x by x, which is equals to 1, and it is value of function fx at 0. So from here we can say that our function fx is continuous. Other way to see the function fx is continuous is, we know that the sine function sin x is continuous and 1 by x is also continuous for x not equals to 0, and product of two continuous function is continuous. So from there also you can conclude that the function fx is a continuous function. So fx is a continuous function, and a continuous function is Riemann integrable. So from here we can say that fx is Riemann integrable. And that completes the first part of the question. And the second part is check whether fx on this defined by this, whether it is Riemann integrable or not. It is a modulus function only, and we know that modulus function is continuous everywhere. So from there you can say that it is continuous. Second, f of x equals to mod of x is continuous everywhere. So from here fx is again Riemann integrable. Also, it's better to check proof of this, that is like the results that we have used so far, that is a continuous function is a Riemann integrable, and also the proof of the second one in which we have done that if a function fx is continuous everywhere except at finite number of points, then it is also Riemann integrable, because it like UPSC can ask it in upcoming exams. So this completes our discussion on Riemann integration. In next video maybe we'll start with improper integration. So thank you for watching, and please do like, share and subscribe the channel. Also, if you have any feedback, please do post that as well in the comment section.